Hello there, my name is Ogodino Jude. Welcome to today's physics class. So our subject is physics. The topic is pitch, loudness, and intensity, and also what quality. So pitch, loudness, and intensity goes together, and quality. The class is SS2, week 9. So lesson objective, at the end of the lesson, you students should be able to explain pitch, loudness, and intensity, also explain quality, then explain noise, music, natural and forced vibration, explain resonance and forced vibration, explain stationary waves. So pitch, when we describe a musical note or a sound as high or low, we are commenting on the pitch of the sound. So pitch is actually the musical notes, the position of the musical notes on a musical scale. So voices that are sharp, whenever, let's say, a musician is singing and you hear like a very sharp kind of voice, not loudness this time around, when it is very, very sharp, that kind of voice is what's called a high-pitched voice. For example, those that have the soprano voices, they have a high-pitched voice compared to those that have gruff voices like a bass voice. So a bass voice we know be as high in pitch as a soprano voice. And these things are also what? Relative. Pitch is relative. In other words, the pitch of a sound is judged in relation to other sounds. So what is actually the main component, or what is the main thing that we need to know when we are talking about pitch is the frequency. Now, the higher the frequency of vibration, and you know frequency has to do with number of vibrations over what? Over time. So number of vibration of the molecule. Let's say, for example, air molecules carrying sound wave, the number of vibration per unit time is what determines the pitch of the sound. So those with a high pitch voice means they are vibrating molecules faster than those with a lower pitch voice. So if you go through this note now, for example, a 200 hertz sound has a high pitch in relation to 100 hertz. 200 hertz sound has a low pitch in relation to 400 hertz, and so on. So if you go lower, what I've said before, that pitch depends on what? Frequency. The higher the frequency, the higher the pitch. The lower the frequency of vibration, or the lower the frequency, because frequency has to be number of vibrations over time, then the lower the what? The sound or whatsoever is given, the lower the pitch. So when you double the frequency, you raise the pitch by 1 octave. For calculation purposes, for example, 200 hertz, if you multiply 200 hertz by 2, you have 400 hertz. That is 1 octave for 200 hertz, depending on your first frequency. That gives you your octave. If the first frequency is 50 and you multiply by 2, 1 octave is what? 100 for the 50 hertz. Okay, having said that, let's go to loudness. Loudness is another quality of sound, or loudness is another characteristics of sound rather. So loudness is a subjective quantity also. While a particular volume may be loud for some, same volume may be soft for others. Loudness depends on amplitude of sound. Amplitude of sound. While pitch depends on frequency of sound. So loudness being dependent on amplitude means that the number of molecules that is vibrating, is it vibrating higher mass of molecule compared to another one that is not vibrating higher mass of molecule? A very typical example is your what? Your loudspeaker. Your loudspeaker is made up of what? A voice. Your loudspeaker has this adjoining voice coil. So that voice coil, when you plug it, when the loudspeaker is moving, now the speaker itself is not that big enough to carry that kind of sound. But what happens to the thing that carries it out of the speaker? So those stuff that carry it out of the speaker, they are very high. That is, they vibrate higher molecules. They vibrate higher molecules or higher mass of molecules out so that we hear them as what? Loud sound. Another example is your tuning fork. A tuning fork now is made up of 2 prongs. When you hit your tuning fork with hammer, or let's say with a hard rubber, they begin to vibrate. You may not hear the sound very well except you place it on a table. When you place it on something like a table now, the air molecules around the table will make the sound louder. What has happened there? the vibrating tuning fork is now setting a higher mass of what? Of air that is vibrating, so that you hear the sound louder, just like your loudspeaker. The speakers itself, they are not that loud, but what's it called now? The adjoining cone is made to be what? Wide. So that's big. The bigger the speaker, the higher the mass of what? Of sound, or the higher the mass of molecules of air that will be vibrated to give you the sound you are going to what? To hear. So in essence, what we are saying now is the larger the amplitude, the louder the sound. So for the first characteristics of sound, which is pitch, it depends on frequency. Loudness depends on what? Amplitude. Amplitude. Okay, going to the next one, quality. Now the same notes played on different instruments sound different. Why? You play the same notes on your musical scale now, they have the same notes, but they sound differently. The simple reason is because they have different harmonics and what? Overtones. Now for every instrument, they have their own unique kind of fundamental frequency. And this fundamental frequency gives birth to other integral frequencies. These integral frequencies, you can relate them with overtones or what? Harmonics. Like we are going to be calculating shortly, we are going to see what we mean by overtone and what? Harmonics. For every particular instrument, the basic frequency or the first frequency or fundamental frequency is called the affix harmonics. And the second one, or the multiple of whatever you have, depending on the kind of instrument you are talking about. So some example of the instruments you're talking about: string instruments, you're talking about open air column, the open pipe and closed pipe, and so on and so forth. So these instruments now, they have their own fundamental frequency, and when you manipulate them for sound, they produce other multiple or integral frequencies that comes out from the main frequency. You understand better when we start the calculation. So what are the three characteristics of sound now? Pitch, that depends on frequency. Loudness or intensity of sound depends on the what? Amplitude. That's the higher volume, higher mass of a vibration of air molecules reaching the listener. So this is what we have been talking about. A summary of what we have been talking about: characteristics of sound, loudness. Look at the soft sound. You can see that the amplitude of this sound, see the amplitude has to do with from this normal, what's it called, equilibrium position, we have the amplitude going higher. We have a negative amplitude, positive, negative. So this is the positive amplitude, negative amplitude. You can see that this one is not as high as this. So this one that has a very high amplitude, look at the amplitude from this point to this point, this top here, from the base to the top, is the word amplitude. So this one with a loud sound has higher amplitude. Now let's go to pitch. Look at the low pitch. Look at the number of vibration. This is from this point to this point, gives us one wavelength, and that one wavelength now you can call this one wavelength and two wavelengths. But look at the number of wavelengths we have here: 1, 2, 3, 4. So you can see that this one has a higher pitch because the number of vibration per unit time is higher than this other one here. So you can see now that those that usually that has a soprano voice, that has a sharper voice compared to that kind of gruff voice, are higher in what? In pitch, and that means their number of vibration is what? More than those with a low pitch. Then quality. Look at the quality. Look at the characteristic notes of a particular instrument. This kind of instrument now is more clearer than this one that has its own kind of frequencies. That's harmonics mixed with the original harmony. Yeah, original harmonies or fundamental frequency. Look at this one. It has different frequency. This has a different frequency. So moving forward, noise and music. Music is produced by vibration of regular frequency. Why noise is produced by vibration of irregular frequency? We've already said that any object that can be made to what? To vibrate air molecules around it, that object will be able to produce what? Sound. So if you play music, music is a vibration of what? Regular frequencies. from an instrument, a musical instrument. But noise is when someone is talking, another one is talking at another frequency, different frequency. Maybe someone is scratching something on the floor. What happened is a mixture of what? Irregular frequencies that are scattered, and that comes out to the listener or goes to the listeners as what? As noise. But when you have this harmonious or melodious kind of frequency coming out from an instrument manipulated by the musician himself or those people playing the instrument, what you get in return is what? A sweet melody known as what? Music that have regular frequency. So natural and forced vibration. A natural vibration is one where an object vibrates freely at its own frequency. However, if an object, such as a pendulum, is made to vibrate at the frequency of another vibrator or vibrating phone, a forced vibration is produced. Okay, this is what we are talking about. Look at this first pendulum bulb. This is the Barton's pendulum experiment. This is a pendulum bulb with what? With a large mass. Compare with other pendulum bulb. But you will notice now that the length of each thread is different. So the one that has the same thread or the same length of thread with the driving force will hit this other one. And when it matches this, what happens? Okay, let's read this. The pendulum which matches the length of the driver oscillator oscillates far more than all the others. So this one hits this and sets it into what? Vibration. And this one begins to vibrate at natural frequency. So all the pendulums shake and move a little. This is called forced vibration. This one has made every other one to vibrate. And when they are vibrating at what? Forced frequency. But this particular bulb, pendulum bulb that has the same length of thread with the driving pendulum bulb, we also cause what we call resonance. Resonance because the frequency or the natural frequency of this will be transferred to the natural frequency of this, and they will both have the same frequency, and that will make this one to what? Resonate, while the other one will be forced to vibrate. So what is resonance there? Resonance is a phenomenon in which a system responds at maximum amplitude to an external driving force. This occurs only when the driving force frequencies is equal to, like what we've seen in the what? In that Barton's experiment. So because they have the same length, the frequency of this will be equal to the frequency of this. It will transfer the frequency. For others, will be forced to what? To vibrate. Those ones won't have the same frequency, and that gives us a forced vibration. So another demonstration is if we use a resonating tuning fork. Now a tuning fork that's just stagnant or static, when you hit the prongs of that tuning fork with a hammer or let's say a hard rubber, and the thing begins to vibrate or oscillates the air around it, what happens now is if you put that tuning fork upon, let's say, a table or this kind of let's say material, now we can call this now a wooden box. Let's say you place it on a wooden box. Now what happens now is this vibrating tuning fork will cause this box now to vibrate, and that kind of vibration is known as what? Forced vibration. Now from tuning fork causing this one to oscillate. Now the frequency of this, both frequencies are not the same, so this will what? Vibrate. That is called forced vibration. Now if you bring another box, let's say wooden box, close to the first vibrating box and the tuning fork, what happens now is this box will transfer its vibration to this other one, and when it transfers this vibration to this tuning fork, to the box also causes a forced vibration to the tuning fork that was not vibrating. Let's go through the process again. This first one was not vibrating. You hit with a hammer or a rubber, it starts vibrating. You place it on a wooden box. The wooden box starts vibrating as what we call forced vibration. You bring another one close to it, then it transfers its natural frequency to the frequency of this other box. That means it's going to resonate because they will have the same natural frequency. Now this forced vibration now is transferred to this second tuning fork. Going over it again, vibrating, forced vibration, then resonance, because especially if they have the same frequency. If they have the same frequency, then this will cause this other one to what? Vibrate. So all tuning fork have their own kind of what? Frequency. They have their frequency, specified frequency. All tuning forks don't have the same frequency. So if the second tuning fork has the same frequency, then it will resonate. You get a loud sound that loud sound indicates that there's what? Resonance. There is what? Resonance. So let's go to the next one. Stationary standing wave. A stationary standing wave is a wave that is formed when two progressive waves of equal frequency and amplitude traveling in opposite direction are what? Combined. Let's use a diagram. Now, this is a diagram of a string that, let's say, a guitar string that has been plucked. Now, the molecules of the guitar string begin to vibrate at maximum amplitude, vibrates. Now we have negative amplitude, under positive amplitude. It meets an obstruction and it's reflected back. When it reflects back, they will produce what we call a stationary standing wave. Now, some points will be vibrating at maximum amplitude. Those points are known as antinode, while some points are not what? Vibrating. So in the stationary standing wave, we have 2 points of One vibrates at maximum amplitude, while one does not vibrate at all. So there's no vibration. And that point where there's no vibration is known as the what? The node. Okay, this is what we are saying. When, let's go back, a stationary wave or standing wave is a wave that is formed when two progressive waves of equal frequency and amplitude, they must have the same frequency and what? Amplitude. It can be the same wave that was reflected back, or different waves that have the same frequency and amplitude, then combining together, or using the word superimpose. They superimpose and form this kind of wave structure. So what is a node now? A node is a point on a stationary wave where there is no movement of the medium, where there's no vibration. While an antinode is a point on a stationary wave where there is maximum displacement of the medium. For stationary wave, the following applies. So for stationary wave, this is your node. From node to antinode, this is the point of node. Let's say this middle part is antinode now, if you divide it into two. Node to antinode is what? 1/4 of the wavelength. So that gives us lambda over 4. Then node to node, from this node to this node, or antinode to antinode is what? Lambda over 2. But when you have node, 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 that is a complete wavelength. Look at it. From this node to this node, lambda over 2 plus lambda over 2, that gives us what? Lambda. Then antinode, antinode, antinode gives us what? 1 wavelength. Hope that is clear. Okay, example. The wavelength of a stationary wave is 36.0 centimeter. What is the distance between a node and the next antinode? So let's go through our solution. The solution now, wavelength, the wavelength that has been given to us is what? 36 centimeter. So wavelength is represented by lambda. What is the distance between the node and the next antinode? And we know from this diagram already, the previous diagram, that node to antinode is what? Lambda over 4. So what you simply do now is you say distance node to lambda, which is the same as L, normal length, is equal to lambda over 4. Cross multiply, that gives us what? 36. That gives us 36 over, what is the distance between the next antinode? So that should be lambda is equal to 36 centimeter. Distance L is what? Lambda over 4. So my L times 4 is equal to what? Lambda, right? So my L is equal to lambda over 4. My L is equal to what? 36 over 4. My L will give us 9 centimeters. So that is what we solve. Let's look at what we solve now. This is it. Our lambda is 36. And we know that from node to node is what? Lambda over 2. But what they're asking us now is like, you are getting half of it. Node to antinode is what? Lambda over 4. And that lambda of node to antinode, lambda over 4, just take it as what? Normal length. So if you cross multiply, L times 4 is equal to lambda, and you are looking for L. So divide lambda by 4, L is equal to 36/4, and that gives us what? 9 centimeter. Okay. So the next example. Okay. In a sound wave, the adjacent real fractions and compression are separated by a distance of 17 centimeter. If the velocity of sound wave is 340 meters per second, determine the what? The frequency. Determine the what? Frequency. So, from your previous knowledge, we said from rarefaction to compression is what? Lambda over 2. That is half wavelength, right? So it therefore means now that what was given to us now, we need to get our L. Our L is now lambda over 2, right? So if I'm going to get the lambda, that will give us what? L times 2. So our lambda, which is the wavelength, will be given as what is the length? The length should be converted in 17 centimeters. Our L is 17 centimeters. So convert to meter, that will give us what? 17 over 100, and that is what? 0.17. So that gives us 0.17 times 2. Lambda will give us 0.34 meters. So that's the standard unit. Yes. So the next thing now is, okay, this is what we have been doing now. Refraction, compression. Then we said from one refraction to compression, especially when you're talking about what? Sound wave, is what? Lambda over 2. Refraction to refraction is what? Refraction to refraction should give you the full lambda itself. So this one now is lambda over 2, L over 1 equal to lambda over 2. When you cross multiply, our lambda, which is the wavelength, we give up because they give you the normal length. The experiment was performed using measurement of ordinary length, but if you want to relate it in terms of wavelength formula, you need to what? Cross multiply or relate the length to whatsoever has been given to you as refraction and what? Compression. So that gives us L times 2, 0.17 times 2, and lambda gives me 0.34 meter. So we know that our wave formula is V equal to what? F lambda, where this stands for velocity or speed of the traveling wave, frequency of vibration, lambda, wavelength. So what are we actually looking for in that question? Let's go back to our slide. So determine the frequency. So if you're looking for frequency, we divide both sides by lambda. So F will give me V over lambda. F will give me, they give us 340 meter per second over 0.34 meter. So F will give me 340 00 over 34. So my F will give me 1000 hertz. So let's see whether that's the answer. 1000 hertz. So distance between successive refraction and compression is lambda over 2. Lambda over 2. So refraction to refraction should give you lambda. Now, example 3. The velocity of sound wave at 27 degrees Celsius is 360 meters per second. Its velocity at 127 degrees Celsius is given as what? So you remember, or if you recall, in one of our classes, we said, or let's write out the parameters first. Example 2. The parameters given to us, or data given to us, T1 is equal to 27 degrees Celsius, convert to Kelvin. T2 is 127 degrees Celsius, convert to Kelvin. Then speed V is equal to 360 meters per second. Okay. Now, recall that V the velocity or speed of sound is directly proportional to square root of its temperature. So V is equal to K root T. Now make K the subject of the formula, that will give us V over root T. Now, if you remove K, it therefore means you can relate V1 over root T1 equal to V2 over root T2, right? So if we interchange, that's the same as V1 over V2, this one taking this position, this one taking this position becomes root T1 over root T2. So this, if you are converting to Kelvin, you add 273. So 27 plus 273, that should give us what? 0, 300, 273, 57, yeah, 300. Then this one should give us what? 400 Kelvin. So our T1, V1 has been given to us as what? V1 has been given to us as 360. Let's go back to the slide and see what was given to us. Okay, V1 was given to us as 360. So V1 is 360. We are looking for V2 is equal to square root of T1. What's the T1 there? Square root of 300 over square root of what? 400. So this means V2 is equal to what? 360 times root. If you cross multiply root 400 divided by root what? 300. So you proceed from there. That is how to solve that. Then using your what? Punching your calculator very well, you are going to arrive at your answer. Let's see the answer on the slide. So this is what you are going to get. You are going to get what? 240. You are going to get 240 meters per second. So vibration in strings. So moving over to another subtopic, vibration in strings. We have fundamental frequency and harmonics. Okay, this is the diagram of vibration in strings. Now, in a string, let's go to the next one. In a string, for example, we have what we call node. Let's derive it on the board. So the first one, let's say this is a barrier and a string vibrates. Let's deal with the first loop. We have node, node. And remember we said that node to node is what? Lambda over 2. If someone was performing this experiment and let's say we use a meter rule or whatsoever ruler you have around, use it to measure and you have the length here. Equating this length to the wavelength that we are going to get here. So remove node to node, L is equal to lambda over 2. When we cross multiply, our lambda will give us what? 2L, right? Now we know that V is equal to F lambda. This is what? The formula that has to do with wave or wave formula. So from V equal to F lambda, if I make it, because we want to know the harmonics and overtone that occurs in what? A string instrument. So we are dealing with the first loop first. So if we call this one out, F is equal to V over lambda, right? Making F the subject of the formula. So our F will give us V over, what is lambda here? We have 2L. 2L. So that is the first frequency. F is equal to V. This is your first harmonics. Okay. Now, what if we have two loops? So let's take a look at two loops. We have node, node, node. So from node to node, lambda over 2. From this node to node again, lambda over 2. If you add lambda over 2 plus lambda over 2, look for the LCM. What are you going to get? You are going to get what? Ordinary lambda, right? Now, if you measure from this point to this point, that acts as a barrier or obstruction, this first obstruction to this other obstruction, then that gives you your what? Your L, your length. So equating L to lambda. Before I even equate L to lambda, let's bring out something. Let's say lambda over 2 plus lambda over 2. Let's look for the LCM 2. That gives me lambda plus lambda, 2 lambda over 2. So that will give us ordinary what? 2 lambda over 2. Now, if I divide now, 2 divided 2, that gives me your lambda. That was what I was saying before. Equate it to this L, because from this place to this place, this wavelength are related to the L. So recall that F is V over lambda, right? So F will give us what? V over, remove this now. Remove your lambda and put L. You understand? Okay. Let's go to the third loop now. And that is where I will stop. You can continue at home after the third loop and check what we are going to derive now. So let's make this one triple. 1. I'll do my drawing. So we already know that this place is what? Node, 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 node. Lambda over 2. Lambda over 2, which is the same thing as what? Lambda, right? Then what is this remaining one now? Lambda over 2. So if you look for the LCM, and if you measure from here to here, let's call it our ordinary length. So let's look for this first. Lambda over 1 plus lambda over 2. That gives us 2 lambda plus what? Lambda. That gives us 3 lambda over 2, right? So if I equate it with L, L is equal to 3 lambda over 2. Cross multiply. So if I cross multiply, that gives me 2L is equal to 3 lambda, right? So lambda now, let's divide this side by 3. 2L is equal to 3 lambda, divide by 3, divide by 3. Sorry. This cancel this. This lambda will give us 2L over 3. So relating it to F is equal to V over lambda, F is equal to V over 2L over 3. And at the end of the day, F will now give us this 3 will move upward when you divide. So that will give us, okay, let me make it simple. No need to hurry. So V over what? 2L over 3. What does this mean? F is equal to V divided by 2L over 3. That's the meaning of that. So our F now becomes what? V times 3 over 2 lambda. So F is equal to 3V over 2 lambda. So what did we actually get now? The first one, F for fundamental frequency, we got what? V over, let's go back and recall what we got. Okay, the first one have V over 2 lambda. The second one, let's call it F1. We got ordinary V over lambda, right? But I can put 2 here and 2 here because we have 2. I'm manipulating right now because 2 cancel 2 will give us what? 1. So F3 will now give us 3V over what? 2 lambda. So what do you see that is similar to everything here? There's something we're going to bring out now. 1 out, 2 out, sorry, 3 out. So if FO is equal to V over 2 lambda, then F1 is equal to 2 V over 2 lambda. If you bring 2 out, this is V over 2 lambda, which is FO, 2FO, F1. So this is not F3. F2 will give us to what? 3FO. So it therefore means now, from what we have done, that we can now say that the fundamental frequency of a string instrument, the fundamental frequency is FO. The next harmonics, which is this is the first harmonics. The next harmonics is what? 2FO. The next harmonics is what? 3FO. If you continue, you are going to have what? 4FO. So 1, 2, 3, 4, etc. and so on. So this is first harmonics. This is second harmonics. And this is what? Third harmonics. Then this is your first overtone. Your second harmonics is your first overtone. So like what I was saying now is FO 1 into V into 2L, 1 into V over 2L. Look at this one again, 2 into V over 2L, F2 is equal to 3 into V over 2L. So if FO, look at it now, FO is ordinary V over 2L, V over 2L, right? Now, if 2 came out and you have V over 2L, what is that going to give us? 2FO, 3 into V over 2L, 3FO. So I'm saying now that for a string instrument, the first one, FO, is your what? Fundamental frequency. The second one is that's your fundamental frequency, and it's called first harmonic. The second one is your second harmonic, third harmonic. So if you're talking of harmonics, the first is first harmonic, second harmonic, third harmonic. But if you're talking of overtones, the second one is your first overtone, while the next one is your second overtone. So this is what we are saying. Let's go to the slide. Okay, look at what we are saying. F for fundamental frequency, first harmonics. F1 is equal to 2F for first overtone, second harmonics, like I've said before, and so on and so forth. So let's see this question. A vibrator of frequency 60 Hz is used in generating transverse stationary wave in a long thin wire. If the average distance between nodes on the wire is 45 centimeters, find the speed of the transverse wave in the wire. So this particular question has been given to us. We are going to write out the So the parameters given to us, example 3, we are given the frequency, vibrator frequency 60 Hz, so frequency is what? 60 Hz, is used to generate transverse stationary wave in a long thin wire. If the average distance between nodes are, so distance node is what? 45 centimeters. Find the speed. We are looking for V. We are looking for the speed. So already we know that from node to node, should be what? Lambda over 2. So our L is what? 2. So if we cross multiply, that gives us what? Lambda is equal to 2L, right? Now, our 45 centimeter is not in standard unit, so you need to convert to meter, and that is what? 45 over 100, and that will give us what? 0.45 meter, right? So we know that V is equal to F lambda, and we're looking for V, the speed. And they've given us the fundamental frequency already. So V is equal to, what's the F there? 60 Hz times the lambda is 2L. So we can also say that this one is same thing as FO times 2L, because already we said that lambda is 2L. So that's 2 times the L that was given to us, 2 times, what's the length now given to us? Two times 0.45. So when you multiply, you get your final answer. So that is it. 2 times 0.5, then, and that is our answer. So 2 times 0.5 will give us 9, and that's 0.9. 0.9 times 60 will give us what we have here. So example 5. Find the frequency of the first string harmonics of a piano string of length 1.5 if the velocity of the wave on the string is 120. So what are the parameters given? So the parameters given to us is length has been given as 1.5 meter, length of the string. So we need to get the wavelength when the string starts vibrating. If the velocity of the wave, velocity is equal to what? 120 ms minus 1. So find the frequency of the first 3 harmonics of a piano string of length 1.5. So if you are going to use the fundamental frequency, we know that fundamental frequency must derive from node to node. So our node to node is lambda over 2, meaning that this place is our length. So change node to your length is equal to lambda over 2. Your lambda is what? 2L. So if your lambda is 2L, then it therefore means that our FO, our lambda will now give us 2 times, what is your F? 4.5. Your lambda will now give us 3 meter, right? 2 times 1.5 is 3 meter. So V is equal to F lambda, F is equal to V over lambda, F is equal to, what is your V? 120 over 3. And the F you are looking for is what? Fundamental frequency. So that's F subscript naught. And that gives us what? So this is what I was explaining. We said now the length is 1.5 meter, our velocity is 120 meter per second. And we said they didn't tell us whether it's from node to node, but from the question, the fundamental frequency, when we derive, is from node to node that get fundamental frequency. After that, every other vibrating point will be greater than node to node. So that's why I related your node to node to your length. So from one node to another node is lambda over 2. That's wavelength or half wavelength, which is lambda over 2. When you cross multiply, you get your lambda. Why are we always getting lambda from 2D? Because the formula for wave does not have ordinary length, but in terms of lambda. So you need to convert that ordinary length given to you to what? To lambda. So that is what we are doing here. And if we make this one the subject of the formula, we are going to have V over lambda. So F naught will give you 120 over. By the time you multiply this by, we didn't convert this one because it's in meter, not centimeter. So when you multiply, you get 3. So your F naught will now give me what? 40 hertz. But that's not all. They said we should look for, I think it's harmonics of overtone. So what did they want us to do? They said find the frequency of the first 3 harmonics. So the first 3 harmonics, you should know now that the first harmonics is FO, second one is 2 FO. So how many do they want? First 3, 3 FO. So 1, 2, 3. If our FO is 40, then 2 times 40, 80. 3 times 40, 120. All of them is what? In hertz. So 40 hertz, 80 hertz, 120 hertz. So that is that for that particular one. Sorry. I'm going to the next one. Okay, that is it. First 3 harmonies. Okay, first 3 harmonies. The first 3 harmonies is this, and this. The first one is the first harmony, second harmony, third harmonies, except they said first 4 harmonies. Okay, so that is the end of today's class. Hope you really understand what we discussed today. So until we meet again in our next class, I still remain Mr. Ogodino Uchi Jude.